Hello friends, welcome back to Recitation Math 141 Summer 2020. I hope that everybody is doing well and feels good about the exam which they took on Thursday of this week. We have episode 14 in store for you today. We are going to introduce one of the most important rules in all of calculus, L'Hopital's rule, perhaps the greatest name rule. I know it's just named after a person, but come on, how awesome is that name? And in particular, we're going to be taking some pretty sick limits today. And by sick, I of course mean awesome. It's a pun because L'Hopital is kind of like hospital. In fact, lots of people just call this the hospital rule because it's easier to say. And that is perfectly fine with me. We have two sections in store for today, so finally getting back to two sections after a couple of relatively shorter homework assignments with just one section. Section 4.5 is where we learn about L'Hopital's rule, which is used to address what we call indeterminate forms. Then in section 4.6, we do some applied stuff, which I know Mackenzie is super excited about. I hope that you all are excited about it as well. We start to see some pretty cool applications of calculus, and we've got two in store, which we're going to do in this video. So, with that said, let's get going. I think we're going to hopefully get through 5 problems today. The first couple won't take as long as the last couple of videos. Those have been taking quite a while. However, the last couple of problems, these applied optimization problems, I'm sure will take some time. So, we're going to start with a few L'Hopital's problems. And first, we are going to use L'Hopital's rule to find the following limit. Something which I should note, I encourage you throughout this video. I will try and make it abundantly clear, but I hope that you can also pay specific attention to this. Try to see and make sure you're understanding why we are using L'Hopital's rule in the situations that we are. L'Hopital's rule is a great tool, relatively straightforward to use, right? Just take the derivative of the top, derivative of the bottom. That's something which we know how to do now. So, you can find yourself tempted to use it sometimes in situations where you shouldn't. And with great power comes great responsibility. So make sure that we are not using this in situations where it is uncalled for. Our first problem today will be the 5th problem on the homework, which asks us to use L'Hopital's rule to evaluate the limit as x approaches 0 of 3x squared over 2ln secant x. So, I'm going to try and do this, I think, for all 3 of these L'Hopital's problems. So, why L'Hopital? Why do we need it here? Well, in this case, remember there are several indeterminate forms which limits can take. So let's see what we have going on here. Well, if I plug in x equals 0, then my fraction becomes 0, right? 3 times 0 squared. Now this denominator, this is going to be a little bit trickier, so let's see. So 2 ln secant of 0. Okay, well, secant of 0, I am just 1 over cosine of 0. And cosine of 0, we know, is 1. So that's 1 over 1. So that's 1. And now I have ln of 1. Let's see, so ln of 1. Well, this is asking, what power do I raise e to? Raise e to get, in this case, our input 1. And e to the 0 power, it turns out, is 1, right? Just about anything to the 0 power is going to be 1. So this denominator as a whole is 2 times 0, and so this comes out to be 0 over 0. And so that is why we use L'Hopital's rule, because 0 over 0 is one of our indeterminate forms. This one and infinity over infinity are probably the two most common ones that you'll see, but of course there are others, and we'll touch on at least one other form in this video. Okay, so that's why we need to use L'Hopital's rule. Again, that's important because whenever you take a derivative out in the wild, it's probably not going to tell you, hey, use L'Hopital's rule on me. That's going to be something that you're going to have to identify. Okay, so what we're going to do now is we're going to take the limit. So we know that we have this indeterminate form. So what we can do is we can take the derivative of the top and the bottom. So limit as x approaches 0 of 3x squared over 2 ln secant x equals, okay, so that's equal to what happens if I take the derivative of the top and bottom. Well, the derivative of the top, that one's not so bad. That's just an application of power rule. So that's just 6x. Now my denominator, oh boy, that derivative is going to be a bit trickier. Let me step aside. d dx of 2 ln of secant x. Okay, well, let me see. So first, I get 2 over secant x. This is because of the derivative. So because the derivative of ln of x equals 1 over x, right? So I'm putting a 1 over the inside, 1 over secant x, and I'm leaving the 2 alone out front, so it moves to the numerator. And now I need to multiply this by the derivative of secant because of chain rule. And as you all know, I'm just kidding, you might not know this one, but it's a good derivative you should know. The derivative of secant is secant tangent, so this right here is the derivative of secant. And so if I simplify this, I'm going to get some canceling secants, and it looks like I'll just have 2 tan x. Okay, so now let's jump back up to our fraction here and plug that in, 2 tan x. Okay, well, let's go ahead and simplify a little bit. I can cancel out 6 and 2, so this is just the limit as x approaches 0 of x, nope, excuse me, 3x, and also that should look like an x, 3x over, now that 2 is gone, and I just have tangent x. Okay, so again, let's try plugging in x equals 0 again. So plug in x equals 0. Let me box off this little region here because this was side work. If I plug in x equals 0, then I get 0 again, 3 times 0, over tangent of 0, and tangent is sine over cosine, and sine of 0, well, that's 0, right? So this comes out to just be 0 over 0 again. Which means, let's do this, we'll do this L'Hopital in a different color. No, we'll stick with it. We'll stick with red. Which means that we have to hit it again with L'Hopital's rule. Okay, so there's no rule saying you can't do L'Hopital's rule more than once. You absolutely can, and that's actually pretty common. So we use L'Hopital's rule again. Okay, and so we have the limit as x approaches 0 of 3x over tan x. Okay, well, this is going to be the limit as x approaches 0. Let's see, the numerator, if I take that derivative, then I just get 3. The denominator, again, we all know that derivative, right? The derivative of tangent is secant squared. Again, that can be kind of a tricky one that unfortunately you do have to memorize, but I do encourage you to go ahead and memorize that. I know it's tricky, but it will make your life easier in moments like this. So now, let's try one more time. I say one more time, maybe we'll have to do it again, I don't know. But let's try plugging in x equals 0, and in my numerator, I just get 3. In my denominator, well, we just mentioned a moment ago, right? We said that secant of 0 here, we said that secant of 0 was 1. So secant squared of 0, well, that's 1 times 1, and that is 1. And a normal person likes to write this as 3 rather than 3 over 1. And so that's our derivative. Or excuse me, our limit. Okay. So let's review here. We wanted to use L'Hopital's rule to find this particular limit. The reason that we needed to use L'Hopital's rule is because whenever we just plugged in the value, in this case x equals 0, we got this indeterminate form of 0 over 0. So we took the derivative of the numerator, the derivative of the denominator, and then we tried again to plug in the value and take the limit, but we got 0 out of 0 over 0 again. So once again, deja vu all over again, as the legendary Yogi Berra said. We took the derivative again of the numerator and the denominator, and we were left, this time we were able to plug in our value and things worked out beautifully. So be persistent with L'Hopital's rule. Sometimes things don't work out immediately, but if you keep trying, they will eventually sort themselves out. Next up, let's look at problem 8. This one, again, tells us to use L'Hopital's rule. I think I misspelled it. Yeah, I misspelled it here. I put an S. Thankfully, math, and I capitalized the L out front. Now I'm reading this directly off the computer screen, so I'm sure that this one is correct. Don't worry about spelling. Spelling does not count in mathematics. Well, it does count to some extent, in that if I was trying to spell, for example, if I was trying to spell like 1, and I spelled it like this, TWO, well, yeah, then spelling would matter, but you get the idea. So the limit which we want to evaluate this time, we're going to now approach x, we are now going to look at what happens as x goes to infinity. We have ln for x minus ln x plus 8. Now there are possibly two things that are coming to mind right now. First of all, how can we have an indeterminate form if we have something minus something else, right? Like that doesn't seem indeterminate. Indeterminate is usually like 0 over 0 or infinity over infinity. So why L'Hopital in this case? Well, this actually is an indeterminate form. And the reason that this is and the way that this is an indeterminate form, well, if we plug in x equals infinity, I know that we technically can't plug in infinity, but you know what I mean here, I think. So if I plug in x equals infinity, well, then this comes out to ln of infinity minus ln of infinity. So ln of infinity, this is asking, well, what power do you raise e to get infinity? And, well, geez, a really, really, really big power. In fact, this is just infinity minus infinity. And this is indeterminate. Indeterminate. The reason that this is indeterminate is because, do I want to get into this? The basic idea in terms of why this is indeterminate is that if I could, in theory, if I wanted to look at the limit as x approaches infinity of 2x minus x, well, if I plug in infinity, then I'm going to get infinity minus infinity, and I'll get infinity. Or, excuse me. Right, then I have infinity minus infinity. But of course, we can see that this limit is actually, really, it's just the limit as x approaches infinity of x, and that we know for a fact to be infinity. Okay, so in this case, I'm going to call this A real quick. In this case, we have a case where we have infinity minus infinity, and then the limit comes out to be infinity. What if I have the limit as x approaches infinity of x minus x. Well, then again, technically, if I just plug in infinity for both functions, then I get infinity minus infinity again. But clearly, this is just the limit as x approaches infinity of 0, and that is 0, right? So I've already got two different answers here. Even though I got infinity minus infinity, that isn't enough information. I've got two different things here. So that alone tells us that it's indeterminate, but just because I'm feeling crazy, what if I did x minus 2x? Well, again, if I just plug stuff in, I'll get infinity minus infinity. But this, as you can see, is just the limit as x approaches infinity of negative x, which is negative infinity. So now I've got three different cases where I've got infinity minus infinity, and I've got three drastically different limits. I got infinity, 0, and negative infinity. So three entirely different limits. Not even close. So that's why this is indeterminate. That's why infinity minus infinity is indeterminate. So let me go ahead and rewrite our limit, because now it's all the way up there. So limit as x approaches infinity, we have ln for x. So now that I've resolved this first question, which you surely had, which was why the heck do I need L'Hopital's rule? Why is this indeterminate? Your second question is, how am I going to use L'Hopital's rule when I don't have a gosh darn fraction? Right? WTF, Bailey, WTF, where's the fraction? Right? Don't I need a fraction? I can't take the numerator, the derivative of the numerator and the denominator if I don't have a numerator and denominator. Excellent question. And observe, we can use our fancy logarithm rules. So recall that ln A minus ln B equals ln of A over B. So what I can do is I can rewrite this as the limit as x approaches infinity of ln, and then I can write 4x over x plus 8. And you might say, well, this, it's not really a fraction, it's ln of a fraction, right? That itself isn't really a fraction. Well, because limits are super well behaved, let me block off my WTF. Since limits are so well behaved, I can move that limit inside the fraction, 4x over x plus 8. And now we're talking. Now I've got me a fraction. And indeed, if I try to take this limit here, this thing here, I'm going to get infinity over infinity. So even this limit, I can't just immediately say what it is. So this is where we're going to actually apply L'Hopital's rule in this case. Okay, infinity over infinity, remember, is another indeterminate form. So now this is, sometimes I've seen people write, they put an equal sign and they write LH above it to indicate that they're applying L'Hopital's rule. So I guess I'll do that here. So I'm going to apply L'Hopital's rule now. This is ln of the limit as x approaches infinity of, take the derivative of the top and I get 4, and the derivative of the bottom and I get 1. Well, now this is just a constant. This is just ln limit as x approaches infinity of 4. And what's the limit as x approaches infinity of 4? Ah, yes, that is just 4. And so we have ln of 4 as our solution. Bada bing, bada boom. H2O. So let's review this problem real quick. Again, this doesn't immediately jump out as a L'Hopital's rule problem. The previous problem, I think it would take us a minute to check this denominator, the ln of secant of x, but it certainly kind of gives off L'Hopital's rule vibes because we have a fraction, right? We have this fraction, whereas this problem, we don't have a fraction immediately, and so it's much less obvious. But whenever we plug in infinity, sure enough, we do get an indeterminate form. The reason infinity minus infinity is indeterminate is that alone doesn't give us any information about what the limit could be. It could be a number of things. Excuse me. But we can use our fancy logarithm rules to reduce, to give us a fraction, which we can hit with L'Hopital's rule then. And then from there, the actual application wasn't so bad because both of these derivatives, the numerator and denominator, were fairly straightforward. Okay. Wonderful. Next up, our final L'Hopital's rule problem of the night or day or whatever time you are watching this. For me, it's night. As you can see, I started a little bit late tonight, as you can see in the corner. So we are going to find the limit. Ooh, this time they don't tell us that we need to use L'Hopital's rule. I wonder if we're going to have to use L'Hopital's rule. I actually don't remember off the top of my head. Let me see. Limit as x approaches infinity, 1 plus 2x, 5 over 2 ln x. Okay, so the first thing that we're going to do here is, as always, as I hope you've kind of developed this intuition, the first thing that you're going to want to do pretty much any time that you take a limit is plug in your thing. Again, in this case, I'll put plug in quotes because technically you can't really plug in infinity because it's not really a number, but we can basically do it and we know what we mean. So if I plug in infinity, let me see, in this bottom part, I get 1 plus 2 times infinity, so that's infinity. And then in the exponent, I have 5. Okay, well, hang on. We said that ln of infinity equals infinity. Again, technically, this doesn't make sense because ln of infinity is technically nonsense. But again, you know what I mean whenever I write that. So this numerator is 5 over infinity, and that is 0. So we have infinity to the 0 here. And this is indeterminate. So it is true that any real number raised to the 0 power is 1, but this goes back to the point that infinity is not a real number, right? Infinity, not a number. Poor infinity, can't be included in the real numbers. It's okay. I won't go into, in this case, why this is an indeterminate form. Basically, you would go through and you would try to find examples like we did up here. Okay, so if you're curious about that, I encourage you to give that a try, or I'm sure there are examples in the textbook or online somewhere. But in any case, we do get an indeterminate form here. So we have to figure out how to go about taking this limit. Well, in this case, just like last time, we can't immediately take, we can't immediately apply L'Hopital's rule. Right, I don't see a fraction anywhere. Immediately apply L'Hopital. I capitalized it again. Sue me, L'Hopital. We can't immediately apply L'Hopital's rule because we don't have a fraction. Because no fraction. We have a fraction in the exponent, but that's not quite enough in this case. So the trick, and this is a very special trick, which you might not come up with if you haven't seen it before. So I hope that you saw it in the textbook or perhaps in Mackenzie's video, or you're going to see it now for the first time. We're going to bring that fraction down, the fraction down from the exponent, fraction down from exponent, and you're probably saying, Bailey, what the heck? We can't just bring a fraction down. We can't, but we can be clever by taking the natural log. Okay, so hear me out, or watch me out. No, yeah, it is a hear me out in this case. So instead, let me take the natural log of this. Okay, so let me take the natural log of our limit here. And then I have the natural log of, or excuse me, how do I want to do this? I want to do, no, this is what I want to do. I'm going to write it. It's the same thing, basically. But I'm going to write, let's take the limit as x goes to infinity of the natural log, so let me put that in parentheses, the natural log of 1 plus 2x yeah, 1 plus 2x to the 5 over 2 ln x. And the reason that I said it didn't matter a moment ago whenever I started to write, let me put this, I want to be clear for a minute. This is in parentheses as well, like this. Like the exponents here, this exponent is inside the natural log exponents. Now, again, the reason that I said I started writing ln and then I decided it didn't really matter, well, because limits behave nicely, this is the same as the natural log of the limit as x goes to infinity of wait a minute, how do I want to, no, excuse me. Let's continue with the way that we have it written. Yeah, let's continue with this. Okay, so what I can do now is I can write the limit as x approaches infinity, and with another natural log trick, I can bring this exponent down now so that I have this. Okay, so the rule that I'm using here is that ln of a to the b equals b times ln of a. Okay, so that's the ln rule that I'm using there. And it's very helpful in this case because it allows me to bring that exponent down. Well, now I can just algebraically rewrite this as a fraction now, as 5 times ln 1 plus 2x over 2 ln x. And what I'm going to do, as always, whenever I want to evaluate a limit, I'm going to plug in the value. So in this case, plug in infinity. And I'm going to get 5 times ln infinity. Well, ln infinity we said was infinity. And for that reason, both the numerator and denominator come out to be infinity. And so this is also indeterminate, right? We've already talked about this one. And so we have to use L'Hopital. Oh, that R is too close. There we go. Okay, so we have the limit as x approaches infinity of 5 ln 1 plus 2x over 2 ln x. I'll do that thing again where I write equals and I write LH over it to indicate L'Hopital. You don't have to do that by any means. But I'm doing it here to help you follow along. So if I take the the derivative of the numerator and the denominator, let me see, the derivative of that numerator, well, the derivative of ln says do 1 over the inside. So in this case, it's going to be 5 over 1 plus 2x. And then I have to chain and multiply by the derivative of 1 plus 2x, which is 2. Now I'm going to put this over the derivative of the bottom. Again, the derivative of ln of x is just 1 over x. In this case, there's no chain rule to do, and so I just have this. 2 over x in the denominator. Okay, there's fractions on fractions here, fractionception. So let me rewrite this slightly, and it becomes 10 over 1 plus 2x over 2 over x. Oh, I forgot my limit. Limit as x goes to infinity, please forgive me. Limit as x goes to infinity should be right out front here. And I don't like fractions on fractions. Does anybody like fractions on fractions? I don't. So I am going to multiply by the reciprocal instead. So instead of dividing by 2 over x, I'm going to multiply by x over 2. Limit as x goes to infinity of 10x over, that becomes 2 plus 4x. Okay, so let's try this thing again. Plug in x equals infinity, and I'm going to get infinity over infinity again, right? 10 times infinity, that's infinity, and so is that denominator. So once again, we have to do L'Hopital again. And we have the limit as x approaches infinity of 10x over 2 plus 4x equals via L'Hopital. Let me see, that's just going to be the limit as x approaches infinity of 10 over 4, and that is just 5/2. So our answer is 5/2, right? No! I don't want to totally cross out the 5/2 because it is important. No! This is not our answer. This is not our answer because remember what we did all the way at the beginning. We started by taking the natural log. So, since we took ln at the beginning, we have to undo that. We must undo that. And how do we undo the natural log? What's the inverse of the natural log? We raise e to that power, right? So we're using the fact we must undo that. And let me write out the identity that we're using. So remember that ln of x, this is what I want to do. E to the ln of x is just x. So we're going to raise our answer, raise our limit, in this case 5/2, raise e to the power of our limit. Raise e to power of limit to undo the natural log, which means that our final answer is e to the 5/2. And that is correct. Okay, so everything was good here whenever we got 5/2, but we have to remember that at the beginning, we took the natural log here. Okay, we did this to help us bring this exponent down, and that was perfectly legal so long as we undo it later. Okay? This is different from whenever you say take the natural log of both sides of an equation, because there we have two sides. Here we're just manipulating one expression. We're not looking at an equation at the beginning here. We're just manipulating one expression, and we're manipulating the expression 1 plus 2x raised to the 5/2 ln of x. Okay, so quick recap. We saw this, we plugged in our value, x equals infinity, and we got the indeterminate form infinity raised to the 0 power. We could not immediately apply L'Hopital because we didn't have a fraction, but by using this fancy trick, we were able to get the fraction, get that exponent out front. This is actually a fairly common trick. Anytime that you have a variable in the exponent and a variable in the base, such as in this case, right? We had this x here, and we had this x in the exponent. This is a great tool to help you bring that variable down front. Once we had done our big fancy trick, we applied L'Hopital's rule a couple times, and we found our limit, and then we just went back and we undid our steps, right? We retraced our steps, and we undid the natural log by raising e to the given power. Okay, I still would like to get through two problems, and I certainly will get through them even if I have to go long. They are the final two problems on this homework, and we're going to move into applied optimization. I find these to be quite tricky, to be honest with you. Related rates make sense to me. I know those are generally tricky, but there's something that, for me, they make sense. Whereas these, I look at them and I'm like, oh my gosh, I don't even know where to get started. So usually what happens is I pick out the problems for these, and then I generally try and solve them as I go. I think that's very realistic, and so I like giving that approach. And generally that doesn't lead to any problems. But here, I sat down before I started recording, and worked out both of these so that I made sure that I knew how to do them. This is going to take a little bit of writing. I apologize for that. Printing with a 4-inch margin. 4-inch margin at the top and bottom. And a 2-inch margin at each side. It's very important that we are reading this closely. One of the reasons, this one took me like 3 tries because each of the first 2 times I totally misread it because I was skimming it and trying to read it quickly. So very important that we take our time reading it. And here we go with the question, what overall dimensions will minimize the amount of paper used? Will minimize the amount of paper used. Okay, we are designing a rectangular poster to contain 50 inches squared of printing with a 4-inch margin at the top and bottom and a 2-inch margin at each side. What overall dimensions will minimize the amount of paper used? So the first thing that you're always going to want to do in these kinds of problems is sketch a picture. So many words here, so much going on. Let's actually jot it down so we can look at it. So in this case, let's start with a rectangle. We know that we're going to need, let's make our picture nice and big. Okay, so we're going to have some sort of rectangle here. We have a 4-inch margin at the top and bottom and a 2-inch margin at each side. So what I'm going to do is I'm going to mark off, we'll call it 4 inches. We'll call there and there. I looked at the example problem that they give, and they draw their picture slightly different. That's not at the top and bottom. See, that's why it's important that we are careful here. This is the top and bottom. Well, that's the top, and this is the bottom. Okay, there we go. So I am 4 inches long. So am I, 4 inches. Okay. And then we have these 2-inch margins at each side. So then, what I was saying was the picture that the example problem gives for this one is a little bit different. But this one makes sense to me. This is the most natural, and ultimately it conveys all the same information. So that one is 2 inches, and so is this one. Okay, which means that this shaded region, which I'm going to shade, let's shade it in blue or green. This is the printing region. Like, this is the stuff that we're printing. So it has area, let me see, I think it told us 50 inches squared of printing. Okay, so printing, the area of this part is 50 inches squared. Okay, now what I'm going to do is I'm going to label my 2 sides. So I'm going to label the 2 sides of this printing area as, I'm going to label the height as y. Okay, so let me actually make that more clear what I mean. So this is y, and I'm going to call this x. So far, so good? Okay, so I guess I shouldn't have written 1 because I'm not going to write out explicitly what each step is because it you can't think about it that way, but for me, I kind of just piece it together as I go. So let's look at what information we can gather now. Well, now I can see that x times y is going to be 50 inches, right? X times y, because that's the area of this rectangle. Of the printing region. And this tells me if I wanted to solve for one of them in terms of the other, I can solve this as, which way do I want to go? I suppose it doesn't really matter. I can say that x equals 50 over y. Right? So, well, and let's do a little bit more computation here. The height of the paper as a whole, the poster as a whole, so this height is equal to y plus 8. Right? So I'm going to call this, let's do this. Let's call this h for height, and then we'll call this w for width. Okay, so the height and width here. Well, the height is going to be y plus 8, right? Because it's y, this part, the middle part is y, and then we have 4 inches on either side. So the height equals y plus 8. And the width is equal to x plus 4. Okay. So the width is equal to x plus 4. And I'm going to go ahead and rewrite x here in terms of y. Okay, so we solved for x equals 50 over y, and I'm going to plug that in here. So now I'm going to call, so then the total area that we're printing, so let A equal total area. Okay, so the area of the whole paper, the whole poster. Remember, this is what we want to minimize. Total area of poster, and this is what we want to minimize in this case. Okay, so then A is going to be width times height, right? Because it's just this rectangle, so it's going to be the width, the base, or whatever you want to call it, times the height, h. Right, and so we already have nice formulas for this. So this is 50 over y plus 4 times y plus 8. And now we're going to go ahead and take the derivative with respect to y. Take derivative with respect. Well, actually, let me go ahead and multiply this out first. So let me see, 50 over y times y. The y's will cancel, and that'll just be 50. I'm going to be lazy, and I'll combine that 50 with the 32 here at the end. So then I'll get 400 over y. You can double check my computation if you like, plus 4y. Plus, and then I have that 50 plus 4 times 8 is 32, so that's plus 82. Okay, so the area is 400 over y plus 4y plus 82. So now whenever I take the derivative of both sides with respect to y, the derivative with respect to y is, okay, so that's 400 y to the negative 1. So that derivative is going to be negative 400 y to the negative 2. I should let me mention something real quick. Let me finish taking this derivative, and then let me make a comment. The remaining derivative is just 4, because the derivative of 4y is just 4, and the 82, its derivative is 0. So the comment I want to make, the reason that I solved here for x in terms of y, I got x equals 50 over y. The great thing about that is that allowed me at this point, whenever I want to take the derivative of the area function, well, now this is a very nice derivative, which we can look at and we can find critical points, find its maxes and mins, etc. And then once I find y, so we're going to use this procedure to find the value of y, I can use that to find both my height and my width. Okay, so all that we really need to do is find y, because once we find y, x will be determined. So now to find critical points, remember we're going to find critical points so that we can find where this function, where area is minimized. So find critical points. So this is undefined. So dA dy undefined at y equals 0. dy undefined at y equals 0 because, let me rewrite this, perhaps that will be helpful, equals negative 400 over y squared plus 4. So if y is 0, then I'm dividing by 4. Then I'm dividing by 0. What on earth? I'm dividing by 0. However, we really don't care about y equals 0. Because if y equals 0, then the printing area is going to be 0. And so clearly that in this context isn't going to make sense. Right? We don't care because can't have printing area equal to 0. Printing area equals 0. Okay, so now let's see. So now let's set 0 equal to dA dy. So dA dy equals 0. And we want to set that equal to negative 400 over y squared plus 4. Yeah, plus 4. Okay, let's go ahead and solve for y. Okay, so then we get negative 4 equals negative 400 over y squared. Multiply everything by y squared. Negative 4y squared equals negative 400. Divide everything by negative 4, y squared equals 100. Y equals plus or minus 10. And really, kind of keeping the context in mind again, since y is this height, it's this height of this printing area, well, that height can't be negative, so clearly we must have y equals 10. Okay? So let's go ahead and check whether this is a local max or local min, or anything. Okay, so y equals 10 is critical point. And let's check that using the second derivative test. So d2a dy squared equals, so if I take the derivative of this derivative, where was it? Negative 400 y to the negative 2. Let's see, I get 800 y to the negative 3, or 800 over y cubed. Y equals 10, and this is greater than 0. It's 800 over 1,000, which is greater than 0. And by second derivative test, there is a local, and in fact a global in this case. Well, it's global in the sense that out of all of the y values that we care about, it's the smallest. Local min at y equals 10. So this is the value of y, which minimizes the area of y, which minimizes area. And that's what we want. Remember, that's what we want. So our dimensions then, we're looking for, let's review what we're actually looking for here. We want to find what overall dimensions will minimize the amount of paper used. So overall dimensions means that it's looking for W and H, our width and our height. So W equals 50 over y plus 4. 50 over y plus 4. And we want y equals 10, so 50 over 10 plus 4, and that is 9. Similarly, our height, this is actually an easier computation. Our height, we said, was y plus 8. Y plus 8, so this is 10 plus 8, and that is 18. So the answer is 9 inches by 18 inches. Or 18 by 9. I don't know exactly which one they put first. Okay? So these problems are tricky, and this one certainly is no exception in these optimization problems. So let's just go over kind of big picture, how we went about this. No pun intended, the first thing that you want to do pretty much anytime you have one of these problems is sketch a picture. You'll notice that one of the first things I did is I went and labeled just about everything, right? I labeled X, Y, the printing area, the margins. I labeled the overall height and the overall width. It's always better to over-label than to under-label. So go ahead and label anything you think might be important. Then you want to start writing equations. So you're going to want to write equations generally relating the things of interest, relating the quantities of interest, and you're usually going to be given some other information. For example, in this case, we were given that we needed the printing area to be 50 inches squared. So use that to guide your equation writing. And think, okay, well, that 50 is going to be important, so that 50 is given by x times y. Then you're generally going to want to isolate one of your variables by solving for it. For example, in this case, we solve for x in terms of y. You could have just as well solved for y in terms of x. You want to make sure that you identify what it is that you want to maximize or minimize, and make sure, and then you can write a formula for that. Hopefully with your substitutions, you're able to write that in terms of just a single variable. So here we wrote it just in terms of y. Then you're just basically going to do the max and min stuff, which we did before. Okay, you're going to find the maxes and mins of that function, or whichever ones are relevant. You're going to generally take the context into account. A lot of times, for example, you'll only be looking for positive values, because a lot of times this will be asking for measures of things. And then from there, you can plug everything back in, and you should be golden. But of course, that's all easier said than done. So let's wrap up and do one more problem, the final one on this homework assignment. This one is super fun. So here we go. Pardon my long writing, but I want to get everything here. A silo, base not included, is to be constructed in the form of a cylinder surmounted by a hemisphere. A cylinder surmounted, big words here, go my math lab, by a hemisphere. This will be a fun picture to draw. The cost of construction per square unit of surface area, is 3 times as great times as great for the hemisphere. So it's more costly to build the hemisphere. For the hemisphere. As it is for the cylindrical is for the cylindrical sidewall. Determine, here we go, now we're getting somewhere. So lots of setup here. Determine the dimensions to be used if the volume is fixed. So we know what the volume of our silo is going to be. The volume is fixed at 6,000 cubic units. I imagine that's supposed to be like feet or meters or something, but it's kind of fun to imagine that as like millimeters or centimeters. Just a tiny, tiny, cute little silo. And the cost of construction is to be kept at a minimum. I suppose that makes sense. Construction is to be kept at a minimum. Yeah, let's minimize the cost. Finally, it tells us to neglect the thickness of the silo. So don't worry about how thick the silo is. The thickness of the silo and waste in construction. I guess those are two things that you would want to take into account in reality. But for now, this will do just fine in construction. Wow, that was like a full page of writing. Holy smokes. A silo, base not included, is to be constructed in the form of a cylinder surmounted by a hemisphere. The cost of construction per square unit of surface area is 3 times as great for the hemisphere as it is for the cylindrical sidewall. Determine the dimensions to be used if the volume is fixed at 6,000 cubic units and the cost of construction is to be kept at a minimum. Neglect the thickness of the silo and waste in construction. Oh my goodness, this is a ton of information to try and organize, but let's do our best here. And as before, let's start with a picture. So I will do my best to draw an accurate depiction of a cylinder surmounted by a hemisphere. So there we go. There's a little hemisphere on top of our cylinder. This will work just fine. Now, before we even start labeling this thing, we're going to need some equations. I think that's going to be helpful to help us know which quantities are worth focusing on. So let's go ahead and I'm going to jot down some equations which we're going to find helpful. So first of all, the volume of a cylinder is going to be pi r squared h. Pi r squared h. Even if you don't know that formula by heart, it's fairly intuitive because basically a cylinder, you just take a circle and then you like move it up and down, right? You take a circle, move it up and down, so it's just the area of the circle times however many circles there are, which is the height. So the volume of a cylinder is pi r squared h. The volume of a sphere, that is 4/3 pi r cubed. 4/3. And we have to be careful here because here we are only interested in a hemisphere. So I'll just write hemi. So that's going to be 2/3 pi r cubed since we're only interested in half of the sphere. We're also going to be interested in some area. So let's go ahead and I'll write just A, but I mean surface area here. The surface area of a cylinder is given by 2 pi r h. This one is also fairly intuitive. It's just the diameter, 2 pi r, of a circle times the height. And the area of a sphere is 4 pi r squared. So just as before, we're only interested in the hemisphere, so that area is 2 pi r squared. So the two quantities which we see come up, the two variables, right? We see pi coming up a lot, but that's not a variable, that's just a constant. It looks like r and h. Those are the two things that come up here, right? R, h, R, h, R, R. So we're going to need to label somehow, we're going to need to figure out what r and h are in this context. So h is just the height of our cylinder. So this is h here. And r actually takes on kind of a double meaning here. So r is the radius of the base of our cylinder. Okay, so it's this length here, half the length of the base. But then it's also, in this case, the radius of the sphere. They have the same radius in this case, as you can tell by our eloquently drawn picture. So I think that's really all that we need to label here. It feels kind of wrong. It feels like we should have more to label, but when it comes down to it, those are really what this problem are going to break down to, our r and our h. Let me just call this r, just to be clear, that's just r. Okay, so let's see what information we have. So the volume is fixed at 6,000 cubic units. Well, let's write the volume of our silo. So the volume of our silo, well, it's going to be the sum of the volume of the cylinder plus the volume of the hemisphere, right? It's going to be the volume of the bottom part, and then we still have that hemisphere on top. So we have to combine those two. And we can go ahead and we have that information. So this is pi r squared h plus the volume of the hemisphere is 2/3 pi r cubed. And we know that this is 6,000. Okay, so this really, the second part here is what we're interested in. Okay. Now, just like we did before, we can solve this for one of our variables, and that could come in handy later. So let's go ahead and solve this for h. So this equation here is the same as saying, I'm mainly solving for h because it looks easier to solve for than r. I've got an r squared, I've got an r cubed. It would get kind of messy. So if I solve this for h, solve for h, let me see, I'm going to have pi r squared h equals 6,000 minus 2/3 pi r cubed. Now I want to divide everything by pi r squared, and I get h equals 6,000 over pi r squared minus, okay, well, let me think. If I divide, so that's going to be 2/3. Well, if I divide pi by pi, that's going to cancel. And if I divide r cubed by r squared, I think I'm just going to have r. Okay, so I thought this was going to be uglier finding h, but that's actually not so terrible. It's a little bit ugly, but it's not so bad. It'll certainly be easy to work with, I think. Easy enough anyways. Okay, so that gives us our volume. I think that we're also going to want the surface area, because that is going to tell us how many, like how many resources we need to use. Right, cost of construction per square unit of surface area. So what we're interested, so let's start by finding surface area. So the surface area of the silo is going to be the area of the cylinder plus the area of the hemisphere. And this, let's see, the area of the cylinder is 2 pi r h plus the area of the hemisphere is 2 pi r squared. But notice, we don't necessarily want to minimize A. We we don't necessarily, that might kind of be what it comes down to. We don't necessarily want to minimize A. If we look back at the problem, determine the dimensions to be used, and if the volume is this, and the cost of construction is to be kept at a minimum. So it's the cost of construction that we want to minimize. We want to minimize cost of construction. So we're actually going to need an equation for that. Let's call this thing C. So the construction, okay, well, what information, so in some sense, it feels like the construction is just however much, it's going to be determined by however much area it takes up, right? But we have this additional piece of information that the cost of construction per square unit of surface area is 3 times as great for the hemisphere as for the cylindrical sidewall. What that means is that whenever we are writing our equation for cost, we need to weight the hemisphere part by 3, because that part costs 3 times as much. So the cost is going to be 2 pi r h plus 3 times 2 pi r squared, which we can of course rewrite as 2 pi r h plus 6 pi r squared. Right? And so now we would love for this to just be in terms of one variable. So let's sub in for h. We solved for h earlier. So this is 2 pi r times h is 6,000 over pi r squared minus 2 over 3 r, is that it? Yeah, 2/3 r plus 6 pi r squared. Let's go ahead and simplify this. When I multiply, so so I've got a pi r canceling in this first part. So it looks like that's going to be 2 times 600 is 1,200 over r. Oops, that should look like an r. And then it looks like I've got minus 4/3 4 pi over 3 r squared plus 6 pi r squared. And we can combine the constants in that second part. And also let me go ahead and rewrite this as 1,200 r to the minus 1. I think that's going to help me out in just a minute. And let's see, my constant for the r squareds comes out to be 6 pi minus 4 pi over 3. So 6 pi minus 4/3 pi, that's 18/3 pi. That's 14 pi over 3. I don't need that parenthesis. 14 pi over 3 r squared. Okay, you can check my math if you need to. That 6 pi is 18 pi over 3. So then I just subtract the 4 pi over 3. Now we want to find the mins of this function, right? Find potentially mins of C, because we want to minimize cost. So we're going to do the same procedure that we've done in this video and the previous. Find the critical points. I'll say it, but I'm not going to write it down here. So if we take the derivative here, so dc, we're going to take this derivative with respect to r, because that's the variable we have. So let me see, I'm going to get negative 1,200 r to the negative 2 plus 28 pi over 3 times r, or in other words, if you prefer, 1,200 over r squared plus 28 pi r over 3. Now, this is undefined at r equals 0. So if we were just looking theoretically, and we wanted to find the absolute minimums of this function, if we wanted to find the minima of this function, we would need to investigate that possibility that we could have a minimum or maximum at r equals 0. But we can't have r equals 0 because r is the radius of this silo. And if the radius is 0, well, that means that the silo doesn't exist, I guess. I don't know. So we don't have to worry about that case. And all that we need to do then is set 0. Let me write it this way, actually. We're going to set this derivative equal to 0. So 0 equals 1200 over r squared plus 28 pi r over 3. That should be negative. I lost a negative sign. There we go. All right, so this is the same as saying 1200 over r squared equals 28 pi r over 3. If I multiply everything by r squared, this is the same as saying 1200 equals 28 pi r cubed over 3. Oh boy, now now I'm going to multiply both sides by 3 over 28 pi. I get 3600 over 28 pi, my favorite number of all, equals r cubed. Wow. I can divide both of these by 4, and I get 900 over 7 pi equals r cubed. Great goodness, cubed root of 900 over 7 pi, it looks like, equals r. Oh, and they tell us to round to the nearest tenth. I'm going to leave it here. Round to nearest tenth. So I'm going to wrap up in just a minute, but let me talk you through how we would finish this up, because from here it's mostly just going to be plug and chug. We now have our value for r. You, once you have plugged into a calculator, have determined this thing to the nearest tenth. So rather than this hideous looking thing, you have, I don't know, 10.1 or something nice. Then what you're going to do with that is you found your value of r, right? I should mention, check that we have a min here. Check that we have a min here, not a max. Okay, you can do that with the second derivative test. You can do that using the first derivative test, where you look at a point to the right and to the left of r, whichever you prefer. And once you do that, plug this in to formula for h. Plug into formula for h. And then you're done, because you have both your value of r and your value of h. Okay. So this problem it's certainly more challenging than the previous. For one thing, we need all of these formulas, which I'll admit I certainly did not know all of them off the top of my head. So you need these formulas. Then you need to combine them in the appropriate ways. Okay, we have a lot of information here, and it's important that we recognize where the information comes into play. Just like before, we had some sort of bounding factor. For example, we knew that the volume had to be 6,000, so we used that to solve for one of our variables, in this case h. We then had to find this equation for cost. Okay, so it's important to recognize what quantity you're trying to maximize or minimize. Our intuition might have said area, but in fact, with the information given, we had to use a slightly different formula, which we tried to minimize. From there, just like we've done previously, you find the maxes, and in this case, I suppose you find the mins of that function, and then you're good to go. I hope that you found this to be helpful. As always, I'm open to suggestions.